At this point, we like to make a subclaim. This subclaim says we can lift B2 prime to some vector B2 in this lattice such that the norm of B2 is bounded by a constant that only depends on D and S. This subclaim is easy to prove, and actually we have seen such an argument before. Indeed, so if you look at, if you take any B2 in lambda with pi w of B2 equal to B2 prime, then you consider the norm of B2 minus the closed integer to this quantity, B2 dot product B1 divided by B1, the norm of B1. The scalar multiple of B1, you consider this thing. And this lives in lambda. And its projection onto lambda w is still B2 prime. And we will show that this is exactly what we want. Actually, by the triangular inequality, this guy is less than or equal to B2 minus this scalar B2 dot B1 divided by norm of B1 times B1 plus this thing times B1 minus the closed integer of this is the same thing, minus the closed integer to this part times B1. Okay, the first part is simply the projection of B2 onto W. So this will be same as the norm of this guy. And what is the second part? We know that the distance between number and the integer closest to it is at most 1/2. And 1/2 times B1's norm will be an upper bound for this. So we bound this line by the sum of those quantities. And we know that they are both bounded by a constant that only depends on D and S. We proved that the norm of B1 is bounded by a constant like this at the very beginning. And the reason that why the norm of this is also bounded by a constant like this is given here. So we are good. We proved this subclaim. We proved this subclaim simply by replacing an arbitrary B2 here by this more elaborated B2. But mind you that we are still proving the claim 2. And I said we'll prove this claim inductively. And what we have just done is like the first or second step of this proof. What we are going to do next is that we are going to repeat the argument And you have to recall all we have done so far and think very carefully. Now, we'll prove claim 2 by repeating the argument we've done so far. Let me show you just one more step. Now we replace the original RD by R-1 dimensional space W, and let W prime be the orthogonal complement of this line in W. So this is a subspace of W. This is a subspace that is the orthogonal complement of this guy in W. And again, you can imagine that we'll take a new lattice lambda sub W prime. This is a projection of this lattice through the orthogonal projection of W onto this, the orthogonal complement of W prime. Then the same argument finds a B3 double prime in lambda sub W. And this B3 double prime is bounded by a constant that only depends on D and S. Furthermore, as in what we have shown here by the same argument as in this subclaim, B3 double prime can be lifted to B3 single prime in lambda W such that the B3 single prime is also bounded by a constant that only depends on D and S. Now, let's do just one more step. You lift this guy to lambda at the very, very beginning. And this B3 prime can be further lifted to some B3 prime in lambda through this orthogonal projection, with the normal fit bounded still by some constant that only depends on D and S. And B1, B2, and B3 are indeed linearly independent. In fact, B2 is linearly independent of B1, and B3 is linearly independent of the first two. This is because of our construction. If you remember our construction, each time we project some vectors down, and the projected down vector will still be linearly independent to the previous one. Some argument like this. So this should be very easy to see. And now we will repeat this argument over and over again. Specifically, I mean, we will repeat the argument with rescaled lambda sub W prime. By rescaling, I mean we will rescale this guy so that it is a unimodular lattice. It has covolume 1. And this B3 double prime in lambda sub W prime And the old argument will show you that this B3 double prime has norm bounded above by some constant that only depends on S, D, and S, and also below by some constant that only depends on D and S. Now, we'll repeat this argument over and over again. Eventually, we'll get the following. Eventually, we have a sequence of vectors B1, B2 prime, B3 double prime, all the way to BD, D minus 1 prime. And any B sub j plus 1, j many primes, is orthogonal to B1, B2 prime, all the way through Bj, j minus 1 primes. And the norm of this guy will still be bounded by some constant that only depends on D and S below, and also by some constant that only depends on D and S from above. And this B sub j plus 1, j primes, can be lifted through first pi sub w j minus 1, and second pi sub w j minus 2, all the way to pi sub w, to some vector b sub j plus 1 in lambda, with b sub j plus 1's norm bounded by some constant that only depends on D and S. And this will finish the proof of this claim 2. We can now find the basis of lambda sub w, and by lifting those vectors, by lifting in particular those vectors, we can lift those d minus 1 vectors to a basis of lambda sub w, lift to a basis of, and that further lift to a basis of lambda. So this part further lift to some basis of lambda. And you know that each basis vector is bounded by a constant that only depends on D and S. And that finishes the proof of our claim 2, and thus our superclaim. Actually, we prove our superclaim directly. We simply find the basis B1 through BD through lifting that belong to a given ball of radius depending only on S and D. So this finishes the proof of claim 2 and the superclaim. Now we can finish the proof of the Maa-ler's compactness criterion. It follows that for any lattice lambda in this given subset K as a beginning, remember we want to prove that this K is pre-compact. For any lattice in this K, we can write lambda as G inverse zd, where this G, where this G inverse is in SLDR. Our superclaim implies that the columns of G inverse can be uniformly bounded by a constant that only depends on D and S. And in particular, what I mean by here is really the norm of each column can be bounded by this C sub ds. And in particular, you know that each entry of G inverse can also be bounded by a constant that only depends on D and S. And because the G inverse is SLDR and whose determinant is equal to 1, you know by the Cramer's rule and the fact that the determinant of it is equal to 1, that each entry of G is also bounded by a constant that only depends on D and S. And then it follows from this identification. Remember the space of lattices? Unimodular lattices is identified with the quotient space SLDR mod SLDZ through the following correspondence: that lambda equal to G inverse times ZD corresponds to the radical set SLDZ G. And since each entry is bounded by some constant CDS, we know that K as a subset of XD is contained in the image of some compact subset K in SLDR. So I should emphasize that this last line implies that G is containing some fixed compact subset of SLDR. Because this bond is uniform, then we have this K is containing the image of some compact subset, the same compact subset in here. Namely, K is contained in pi of K tilde, where pi is from SLDR to this quotient SLDR mod SLDZ. But we know that this map is continuous, and the image of a compact subset is again compact. So K is contained in a compact subset. And in particular, because XD is Hausdorff, the compact subsets are closed. The K is contained in the closure of K is also contained in that compact subset. So K will be pre-compact. And that finished the proof of Mahler's compactness criterion. Finally,